Hello, so today we are going to do this problem called path with minimum effort. So the problem says, it's part of Leetcode April challenge. It says that you are a hiker preparing for an upcoming hike. You can like ignore this part of the story, but essentially we have a 2D array of heights. And what we want to do is, basically in each cell we have a value, right? And initially we are situated in 0, 0 position, so right here, and we want to go to the last position, so here, and you can move up, right? You can move either up, or down, or left, or right, right? Left or right. So yeah, typical traversal so far, and what we want is the minimum effort required to travel from the top left here to the top right here. And what's an effort here? So we want the minimum effort, but what's the definition of an effort? So it's the maximum absolute difference in height, so between two consecutive cells. So basically, here the difference is 2, right? Here the difference is 2 as well. Here the difference is 2 between these two, and this here difference is 2. So overall the maximum difference is 2. So for this path, if we take another path, let's say we go left and then go here and then go here and then go down, then the difference here would be 1. The difference here, I think 6, right? Yes, 6, and then here 6 as well, and then here 3, right? So the maximum difference here is 6. And so we choose the one with the smallest one, which is 2. Of course, we can try other paths, but the green one is the right path. So yeah, that's the problem. So essentially what we want is minimum effort to travel from 0, 0 position to the last position, n-1, n-1 position. And we want the minimum effort where the effort is the maximum absolute difference between every two consecutive cells. So that's essentially the problem description here. And now how can we solve it? So one thing you can see here is that they gave us the boundaries of the height, right? Here it's 10 to the power of 6. So we know that it's 10 to the power of 6 the max and 1 the min. Okay, so this would mean that this is the height of one cell, right? Can go at most to 10 to the power of 6. So the worst case, you would have 10 to the power of 6 and 1, right? So the effort, the maximum value for the effort can be 10 to the power of 6, and the minimum value of it can be 0, right? If you have to cell 1 and 1, right? So what this would mean basically is, and we are asked to do the minimum effort, so this basically hints at using binary search. And this is exactly what they give us here in the hints. They said binary search on the k value, which means basically binary search on the minimum effort and try to see what's the minimum value that can get us from the top position to this last position, destination position. Yeah, so that's the main idea here, is to use binary search for the value, and then for finding the for like checking if every value we try to binary search for, if it's feasible, we can just use DFS to see can we get from this position 0, 0 to the last position with an effort of k. So we can use either DFS or BFS for that. So that's what I'm going to do here. I will do it first using DFS, and then after that we can see it using BFS. Okay, so let's get started here. So the first thing we need to do is just our binary search template, right? And so for binary search, what we need to find is the function, and we need to find to define our boundaries, right? So our boundaries, we said the height is between at most 1 and 10 to the power of 6. So that means basically for the absolute difference between cells, the lowest value it can be is 0. The highest value it can be is 10 to the power of 6. Why is this 10 to the power of 6? This is because here this is the max, right? And the min is 1, so at most at the smallest value we can have is 2 cells of value 1, and the difference would be 0. And now we can just do template binary search, and then at the end we return low, and then here we need to calculate our mid value. You can do this just to avoid overflow. We don't need to worry about it in this solution here, but sorry, this is low because the bounds are good, but it's just good to get into that habit. And now we can have our function which checks if we can reach the destination with this mid value, right? If we can reach it, if so, we do something, otherwise we do something else. Okay, so this is where we need to choose what to modify here. Okay, and the way to think about this is to say, okay, what is can reach destination for us here? So can reach destination is basically, can we get from 0, 0 to the last position, which is basically row minus 1, number of rows minus 1, number of column minus 1, with cost, right, or with effort less than or equal to a mid, right, less than or equal to this value. And with this, you can, a good way to think about binary search is to find a pattern of false and then of true values, or the reverse, a pattern of true values and then a pattern of false values. Okay, so which one works for us here? One thing to think about, okay, if we can get from 0 to this with an effort of value, let's say 2, then we can get there with an effort of value less than or equal to 3, right? Because basically just simple 2 is smaller than or equal to 3. So basically, if you have something, we can reach the end with an effort less than or equal to 2, then that's valid for anything bigger than 2, right? Valid for bigger, less than or equal to 4, less than or equal to 5, so it's valid for everything bigger, right? So as mid increases, once we hit a true, we always hit a true, right? So seems like we are closer to this, but let's check with false. If you can't reach with a value of 2, then you can't reach with a value smaller than 2, right? Obviously, because because the absolute difference is the maximum absolute difference between two cells, right? So if you can't reach with a maximum absolute difference of 2, you can't reach with smaller 1 or 0, right? And so that means when it's false, when it was false, bigger values are false, but once it is true, it continues to be true. And so with this here, we can easily find what we should change. So if we can reach destination with a value, that means we are somewhere here, either this here or maybe here or somewhere in between, but in the true values, right? So this is our mid value here, okay? And our low was somewhere here, and then our high is somewhere here, and our low is in another place here, okay? Okay, so what should we change? So we can reach destination at mid. So either it's either we are here or we are here, but we shouldn't go check in these. We know we shouldn't go check in these, right? Because we know these will be true. And so what we do is we put our high at position mid, right? Just in case we were at the first true, we do want to include mid, right? And so what we do here is we set our high to mid, and for low we need to set it to what? So if this was false, so now we are in the case where can reach destination is false. So mid is somewhere here in the false area. Let me just add more false, right? And high is somewhere, we don't care about where exactly. So if mid is in false, then we shouldn't check here. That's not useful, right? We will find always false. So what we need is we need to put our mid in the position after our low value in position after mid, so that we get a chance of finding a true value, right? Because we know at mid it's false. And so what this would mean is we need to set this to, this is mid plus 1. What this would mean is we need to set our low value to mid plus 1. So that's the main idea here. And now we need to write can reach destination, which just checks if we can reach from this 0, 0 to the last position with the effort less than or equal to mid. So let's first write it with DFS, and then after that we can use BFS. And here let's call it threshold, right? Because it's smaller than or equal to that value. And now we can write our DFS. Or actually, let's just call it this, and then this would use a DFS. So we'd have our DFS here. That, of course, needs to have the positions. And here we need to start our DFS with 0 and 0 and pass threshold. Okay. Okay, so now for if we take a look again at our example here, to do DFS, we need to go to the neighbors, right? And so how to do that? We need to so we need to first check if we arrive it, right? And we arrive when I is equal to R minus 1 and G equal to C minus 1. So we need to define these two here. Let's define them here. R and C are equal to the length of heights and the length of the first row of heights. Okay. So if this is the case, that means we arrived. So that means we can reach these values with something smaller than the threshold. So we return true. But if it's bigger, right? If it's bigger or equal, same thing for, that means we exceeded the bounds. So we need to return false. We exceeded the bounds and we didn't reach the position we want. Now we need to walk through the neighbors, the neighbors we are looking for. So I'll call them Ni and Nj, and neighbors are to the left. Or is this to the left? This is bottom row. So to the bottom, going down, and then we'll just do all of them. Going right, going up, and then going left. Okay. And for those, what do we need to do here? We need to check first if these positions are valid. So only if that we do anything. So we'll need to define this function that checks that coordinates are valid. Okay. And now what we need to do is we also need the cost to still be smaller. So we need the cost, which is the maximum absolute difference in height between this cell and its neighbor. We need it to be within the effort, which is the threshold that we have here. And so let's just calculate it. So let's call it diff. It needs to be the difference between the absolute difference between the height of the cell and its neighboring cell. Okay. So if this diff value is smaller or equal to the threshold, right? This is the definition of what we are looking for. Then we want to return true. There is another thing we want to do, which is we don't want to revisit cells. So let's say we already went to, this cell here. We don't want to come back to it by going left here. We don't want to do that. And so we need to have a visited set. And so to do that, we can just define our visited set here, okay, and pass it. And so here we need to have our visited set, and here we need to check that these two are not in visited. Okay. But one thing we also want to do is, just because we want to check valid before accessing, so let's just have this here. And I'll put this down. Okay. Now, if none of these, we weren't able to find any, if we weren't able to find any neighbor, right, with a cost smaller than threshold that is valid, then we need to return false, because that means this can't be accomplished. So we need to return false. Another thing we need to not forget about is adding to visited set, right? So we need to add INJ to our visited set, okay? So that this check works. And that should be pretty much it, except we need to return whatever DFS tells us. We need to return it. And now we need to define our valid function. So we want to just check that the indices here are valid, so pretty straightforward. Just between the bounds. Okay, and now we can run this function. Yeah, so another thing actually we need to do that I forgot to do here, of course with the DFS you need to call on the neighbors, right, to be able to reach the end. So here, let's change this a little bit here. Before doing true, we need to check for DFS of the neighbors, so we need to pass for the neighbor and go with visited and then do pass the threshold, right? Only if that's the case that we need to return. And so just to make this easier to read, I'll do this first, and then this is the cost, and we want to check that the cost is smaller than or equal to the threshold, okay? And only then we return true. Yeah, so this, now let's run it again. Okay, so that looks good. Let's submit it. Okay, so that passes test cases. Yeah, so pretty much just doing binary search and then doing DFS to get to check if we can reach the destination using that cost, so with using values small or equal to that cost, and while doing it with this. Okay, so that's the DFS solution. Now let's change it a little bit and just do the BFS here to get some practice for BFS. So to do that we need to create a queue. So we no longer need, we can remove this and just do it here. So we of course still need a set, but let's start our set with the value 0, 0. And then we need to have a queue for BFS, and also the queue starts out with 0, 0. Okay, and then we need to go through the queue here, and then we need to pop the leftmost element, and this will give us INJ. And now what we need to do is go through the neighbors like we did before with DFS. Okay, so we pop left. We need to add to, we need to go through the neighbors in the same way that we did with DFS. So similar solution, right? I minus 1, j, I, j minus 1, okay. And then we need to check if valid. And we need to check that it's not visited. Then we need to add it to the visited, right? And we need to add to our queue. So append. We need to check here if we reached our destination. So if this is equal to we return true. Now we should check the cost as well, right? So we should calculate cost, which is the absolute value of heights, ij, and then the height for the neighbor, right? And then we need to check if cost is smaller than or equal to threshold, only in that case that we want to explore this here, okay? And that should be it, pretty much, for BFS. So notice we are popping from the front here with pop left, and we are adding to the end. Cool, okay. And now let's just, when we end and we didn't find anything, we can return false. Okay, so this is because of the queue here. We need to define it not as a set, it needs to be a DQ, right? So this will be something like this. And this is the content of it. Okay, so that seems to be good. Let's submit. Okay, so that passes test cases. Yeah, so pretty much here we saw a solution using DFS and another one using BFS. Very straightforward. We can also solve this with Dijkstra, with a little modification where the weights we would use for the weight, we'd use this value here. Yeah, you can try that if you want, but I think this is good enough. Yeah, cool. Thanks for watching and see you on the next one.